feeling pretty confident for you guys in this lesson because we introduced the concepts of semi-log plots back in topic 2.9. Semi-log plots, does this look familiar to you? Yes. Okay, great. We did really well at this, so I'm feeling pretty good. We're going to take it a little bit further and talk about the applications of semi-log plots and what we are getting out of them besides just being able to plot coordinate points. So in a semi-log plot, one of the axes, it's hard for me to say that word, pluralize, is logarithmically scaled. In AP Pre-Cal, we will only be scaling the vertical or y-axis with a logarithm scale. That's why it's called a semi-log, like half-log plot. There is such a thing in engineering called a log-log plot, where both the x and the y is logarithmically scaled. We're just going to do a semi-log plot. So what I want us to do for most of these questions today is highlight the y-axis when we notice that it has been logarithmically scaled, meaning we see that every bunch or band of lines is a power of the base we're using, in this case base 10. A lot of them are base 10. We want to recognize this so that we are getting prepared to know we're working with semi-log plots each time. The other thing we need to learn from this lesson is that in a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. Let me say that again. In a semi-log plot, exponentially functions will appear linear. This is bolded and underlined, but I want you to add the little cloud around it. This is a huge concept from you today. You will be able to eliminate incorrect graphs and find appropriate graphs for exponential functions on semi-log plots if all you do is look for a straight line. Exponential, linear on logs. That's a huge thing. Look for straight lines. Because if you notice, this is a straight line, is it not? And since it's on a semi-log plot, I know that this data is exponential. I don't need to plot it regularly and see it exponentially grow like normal. I just know that an exponential will be linear on a semi-log plot. So this question number 1, after Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people, P, that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Use the features of the semi-log plot above to justify why an exponential model would be appropriate for this data. We're literally just going to write down the reason why this works. The reason would be the semi-log plot appears to be linear. Hello, let me write the word linear better. The semi-log plot above appears to be linear, so the exponential model is appropriate. That's it. If you know on a semi-log plot that the dots go in a straight line, they're representing an exponential function, period. And the reason why that is super helpful to know and be able to justify is for questions like example 2. Which of the following could be the model for P? Well, remember, it's appearing linear, but what kind of function is it? Exponential. So all we need to do is find the exponential function. Is this an exponential function? No. What kind of function is that? Is it? It's linear. So wrong. Don't want that. What kind of function is the second one? Where is the variable?
It's squared.
It's exponential. If the variable is in the exponent, it's exponential. So we're going to hang on to that one. What about letter C? What kind of function is that one? Logarithmic. Is that what we want right now? No. Exponentials appear linear on log. Okay, what about the last one? What kind of function is that? Also exponential. So just literally by knowing the fact that if it's linear on a semilog, it has to be exponential. We get it down to two equations. So we need to figure out which one of these is right. The easiest thing to do here is look for your initial value. On the graph itself, what is the initial value? 2. We know this because the initial value will be your y-intercept when your x value is 2. So we have an initial value of 2. Only one of the equations, B or D, has an initial value of 2. Initial values in exponential functions are found being the number directly in front of the thing with a power. Directly in front of the thing with a power right here is an invisible number 1. That's not what we want. This has an initial value of 1. What is the number exactly in front of the thing with a power here?
2.
That's the one we want. The initial value of 2.
Oh, we're back on doing that.
Correct. Because it's an exponential function. We now, see, this is the thing. We're going back and forth in different function types. Have to keep it all straight.
Okay, let me switch.
Okay. So again, let me walk through this one. We recognize from the graph itself that since the data appears linear on a semilog, it has to be an exponential function. So we got rid of a and c because those were not exponential functions. The x has to be in the exponent. To then go between the two that we had left, we looked at the initial value, which is typically something easy to notice. This initial value is 2. Here's 1, so this is 2. This has an initial value of 1 because there's a 1 in front of the 2 to the t power. This has an initial value of 2 because there's a 2 in front of the 2 to the t power.
So how is that initial value 1?
How is the what?
The initial value 1 for 2.
If you were to write this out, it should be 2 plus 1 times 2 to the t. Directly in front of the thing with the power, there's nothing there, right? So it's a 1.
But it has to be something there.
There always is something there, it's just in the invisible 1. Where on this one, you can see the number in front of the thing with the power, so the initial value is 2.
Okay.
There's even easier kinds of questions that come with this, because remember, we're just trying to get you used to seeing semilog plots. Example 3, it says the table above gives the selected values for function f. Which of the following graphs could represent the data in a semilog plot where the vertical axis is logarithmically scaled? There are 2 graphs on here that are not semilog plots. We need to get rid of them. Is this one a semilog plot? Does it bunch it by powers of 10s? No, get rid of that one. There's no way that could be right because it's not even a semilog plot. Is this one a semilog plot? It actually is. There are 10 lines between 1 and 10 that are not evenly spaced. It is logarithmically scaled.
So is it always like 10 or could it be other number?
It could be another number, but usually it's 10 because of the common log. Like that's an easy log to work with. What about that third one? Is that y-axis logarithmically scaled? No, that looks linearly scaled. That looks like really pretty normal. That's not what we want. Get that out of there. What about the last one? Yes, that one looks normal for us. But do you see how, and I don't know how to really like describe this any other way, but do you see how like they're unevenly spaced?
Yes.
And it gets smaller and then it'll go, and then it gets smaller. That's what's happening here. We only just have one band. A lot of space, little, 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 little. If we repeat it, it'd be a lot of space, little, little, little. That's what you're looking for in a semilog plot. But of course, now we have 2 answer choices left. How do we decide between them? We need to actually look at the coordinate points. Our first coordinate point should be at 1, 40. Is this 1, 40? No. Is this 1, 40?
Yeah.
Ah, okay, so right there, we eliminated it down to 1 answer choice. We looked at exactly the coordinate point 1, 40, which is what we got out of the table.
Wait, so the lines have to be uneven?
Essentially, yeah, the lines have to be uneven for it to be semi-logged. So this concept of being able then to read the graphs once we notice that they're semi-logged comes back. So as a review, you guys have example 4 on the back. We've done this before, so I just want to see what you remember. I'm going to use pink, then blue, then green, then purple, then orange if you want to use my color scheme. Meaning I'm going to plot each of these points in just a little bit. I want you to do it first. I'm going to do it in these colors because I know the color scheme is very important to a lot of us. But I want you to plot these coordinate points on that semi-log plot just to make sure we still got it. We had it earlier this year. All right, if we were doing this one, I would put A, which is 0, 200, like right here. Is that where you put A?
Yeah.
Nice. I would put B at 1, 25, so 10, 20, 25, here-ish. C is 2, 7, so this is 1, 2, 3, 4, 5, 6, 7. Is that where you put yours? Let me see if I can get it there. 1, 2, 3, 4, 5, 6, 7. 3, 3.2, 800. Ooh, 0.2. So if this is 3, 3.2, 3.4, 3.6, 3.84. So we are counting by 0.2s here. So I'm going to go 3.2. Then all the way up to 800, which if this is 100, 200, 300, 400, 500, 600, 700, 800. Should be right here. Is that where we got it? Very nice. Oh, I just hit like 3 lines drawing that, but you get it. And then 4.6. Again, this is 4.2, 4.4, 4.6. If we're going to 1.5, this one's always tricky. This level right here is already 1. This level is 2. So it's in between them. I think the first time I did this, I put it above the next line, thinking 1.5. Remember, 1 is the bottom line here. Okay, so we feel pretty good about the coordinate points. Great. The next step, after we start to recognize semi-log plots compared to regular ones, plot coordinate points, is to actually create the linear models for these exponential functions on semi-log plots. So as we have seen, if we graph an exponential on semi-log, the graph will appear linear. So we want an actual linear model, a regular linear equation to represent this. Given the exponential model a plus a times b to the x, the corresponding linear model for the semi-log plot is given by y equal to log base n of b times x plus log base n of a. And if you're like, that's just mumbo jumbo, Miss Quigley, you're right. Let me make this make more sense to you. What if we wrote y equals mx plus b right underneath there? It's a linear equation. It's just that the slope is represented by log base n of b, and the y-intercept b is represented by log base n of a. The a and the b come from the original exponential equation, and the n is the base that we use for scaling the vertical axis. Just as an FYI, this is usually 10. It can be any base, but we usually semi-log based on 10. 6 feet on the floor, please. Thank you. So our job in these kinds of problems, when we are doing the linearization of these semi-log plotted exponential functions, is to find the slope and the y-intercept of that line. We've been finding slope and y-intercept for a long time. We just need to know, instead of the rise and the run and the initial value, we need to know the a and the b so that we can plug it into log base n of a and log base n of b. So for example, the semi-log plot above corresponds to the data table from example 3, which is on the other side of the page. And just because I think it's helpful to see, that data table was as follows: 1, 40, 2, 60, 3, 90, 4, 135, and 5, 703. That's not a 7. I can't read my own handwriting. 203. Where'd that come from? If you flip your page over, example 3 has this in a table form. I'm just writing it over here because that way we don't have to flip back and forth. We also could have gotten these coordinate points from here. This is 1, 40, 2, 60, 3, 90, 4, 135, but it's really hard to see 5, 203, so I made sure we saw it from the table. If we want an equation for the linear model for the semi-log plot, we need to know A, we need to know B, we need to know N. Easiest one to answer for this is N. What is the scale we are using on the y-axis? 10. So N is going to be 10 because that's the scale of my y-axis. So N is 10. Great. That's a common log. Super easy to use. Now we need to find the A and the B. We have two options. I think I'll know your opinion once I propose these two options for you. If we have a table of data and we need to find the A and the B that represent that data, we can either do it by hand, which is what we did on the last set of notes, or we can use our calculator to do stat edit and run a regression. Which one would you like to do?
You already know.
I already know, but let's go through it. Now, before we get crazy, what kind of function are we trying to find? Linear, exponential, or logarithm? Because we have all three floating around this problem. Eventually, we're going to write a linear equation, but where do the A and the B come from?
Wait, what do you mean?
Where are we getting the A and this B from?
I want to say logarithmic.
I would want to say that too, but it's not correct. It's actually the exponential function, because A and the B come from the exponential function that originated the model. So when we're doing this problem and we're trying to linearize an exponential on a log, that's three different function types. We are using option 0, which is the exponential regression, because we need the A and the B from an exponential to plug them into a log to get a linear. Yes, it's confusing. I know you know how to do this, so I'm going to let your fingers do all the work. You have the table here, 1, 2, 3, 4, 5, and then the outputs that correspond to it. We want an exponential regression this time. I need the A value, and I need the B value. I'll give you a second. Our calculator would tell us that the A value we want to use here is 26.6404. Agreed? And then our B value is 1.5007. Make sense? If we were just asked for the exponential regression, boom, done. But unfortunately, we're asked to linearize this exponential on a semi-log. So now we take this formula that we got in the box above, and it was given to us in this problem, thank goodness. We're just going to plug everything in. You plug the N, the B, and the A into the equation, which means we would have y equal to log base 10 of 1.5007x plus log base 10.
Okay, I have a question.
Yes.
Will we put the 10?
You don't have to, because what is base 10?
Yeah.
It's that common logarithm, right? Yeah, you don't have to. I'm just doing, it's our note, so like where did the 10 go? Might be a question you ask yourself later. It went right there. Yes, ma'am.
I keep resetting my calculator, but I keep getting different numbers, but I'm putting the same numbers in the table.
I'll come check on that later.
What did I do wrong?
Exactly.
From here, what I know about this now linear function is that we have a slope of common log of 1.5007, and we have a y-intercept of common log 26.6404. So what we can do is we can take those two numbers and plug them into our calculator. One at a time, don't put the x in there. So if I typed in my calculator log of 1.5007, it would give me 0.1763. And if I typed into my calculator log base 10 of 26.6404, we would get 1.4255. This will always, by the way, if there's a question about this on a test, this will always come as a multiple choice question. So if the answers look like they have logs in them, you stop here. If the answers look like they do not have logs in them anymore, you evaluate fully. Kilo, what's up?
With the logs, when we're inserting it in the calculator, if it has, how do we put the base number for the logs?
Ooh, great question. If it's not base 10, does anyone remember how to get the log base on the calculator?
Wait, I'm trying to find it. Find the,
It's hidden a little bit.
yeah, that, what the,
It is on the math menu. Everybody hit math. You have to scroll down. It's not on the front screen. But then you can see log base.
oh yeah,
You see it now? Yeah, that was a great question because we haven't needed that in a while. Might want to write that down in case you'd forgotten.
wait, what was it?
Math, and then keep scrolling, keep going. Oh, right there. Yeah, log base.